In the previous two videos, we talked about using both trapezoidal rule and Simpsons rule to estimate an integral that is not easy for us to calculate exactly. And we said, hey, I can use the trapezoidal rule or Simpsons rule to get within a fraction of a percent to the actual or exact integral value. So we learned to use Simpsons rule and trapezoidal rule to help us approximate definite integral values. But we want to know how far off are we? So whenever we use one of these approximation techniques, the issue arises as to, how accurate, how exact or close to the exact number this approximation might be. So this theorem I have presented here for error estimates using the trapezoidal and Simpsons rule, respectively, trapezoidal and then Simpsons. This estimates the error for us, and the error is being just that difference between the approximation we get using our two rules, trapezoidal and Simpsons, versus the actual value of the definite integral. So what we do here is we say, if we're dealing with the trapezoidal rule, we look at the second derivative. As long as it's continuous and we can come up with m, which represents an upper bound for the values of that second derivative, the magnitude, if you will, on a closed interval, then the trapezoidal error, the error with the trapezoidal approximation of that integral, for n steps is satisfied by this equality. E sub t, my trapezoidal error, is going to be less than or equal to the magnitude of the upper bound for the second derivative, the difference of my integration bounds cubed, divided by 12n, the number of steps squared. And very similar with the Simpsons rule, we're just going to use the fourth derivative. And again, m, that upper bound, is going to be the magnitude of the values for the fourth derivative, somewhere between a and b. So the error with Simpsons rule, E sub s, is found to be less than or equal to the magnitude of that fourth derivative, the difference of my integration bounds to the fifth power, divided by 180 n, my step value, to the fourth. So I'm just going to do one example. I'm going to use the Simpsons rule, but it would be very similar using the trapezoidal rule. In this example, we're going to find the upper bound, m, to help us estimate the error for the definite integral using Simpsons rule with a step of n equals 4. And in the previous video, we used Simpsons rule to approximate this integral, even though this is an integral that we can calculate exactly very easily. And we determined with our Simpsons rule approximation that we were only off from the exact quantity, or the exact integral value, by 0.0026, or moving that decimal 2 spaces to the right, 0.26%. So less than 1%. And if we go to apply our Simpsons rule error estimate approximation, we need to find that upper bound first. So we're going to take our function f of x, which is 5x to the fourth, and we're going to calculate up to the fourth derivative. So f prime of x is 20x cubed. My second derivative is 60x squared. My third derivative is 120x, and my fourth derivative is 120. Now, this is a constant value. So that means my m, my upper bound, m, is going to be 120. So remembering here that m is that magnitude of the fourth derivative. Now, we know what my a value is. A is 0, b is 2, and n, which of course was given, n was 4. So if we go to use our error estimation, I should write a regular E, our error estimation with the Simpsons rule, the magnitude of that error is going to be less than or equal to 120. We have b minus a to the fifth over 180 n to the fourth. That was the formula. So I just have to plug these numbers in, and this is going to tell me that I know with the Simpsons error or the Simpsons rule approximation that my error is going to be less than or equal to whatever value we get here. So my Simpsons rule error estimation less than or equal to 120. B minus A, 2 minus 0 is 2 to the fifth, or 32, over 180 times 4 to the fourth. And that value, if we simplify it, is equal to 1/12, or 0.083 repeating. And that means that we know our error is going to be less than 8.3%. And of course, it was much less than that because in the previous example, we were able to calculate the exact value of this integral. And using our Simpsons rule approximation, we were off by less than 1/3 of a percent. Okay, so, but this is just saying to me that if I use the Simpsons rule to approximate the integral, I will be within 8.3% of the exact integral value. So trapezoidal rule, you do it very similarly. You just define your m off of your second derivative, and then we have a slightly different formula. Of course, we said that the Simpsons rule is a better approximation than the trapezoidal rule. So I hope that helps you. If you have any questions, again, the reason we use trapezoidal and Simpsons rules because sometimes we cannot calculate an integral value. Sometimes it's just too hard for us to deal with. And we say, okay, well, I'm going to approximate it and get as close as I can that is acceptable for my future calculations.